Hello everybody, it's Andrew here. Very sorry I can't be with you. I did want to, however, try and give you a quick update on my work at St Denis and the outcomes from the Ccrn funded programme. So I'm going to present work of two students, Edward Bam and Sujata Budhat-Hockey, and many thanks to others who I haven't got time to mention. I'm going to talk briefly then about two topics. The first is frozen soil infiltration and runoff generation, and the second is groundwater surface water interactions. And this is all field work at St Denis. So, as we all know, rainfall, shown at the top, tells you very little about runoff, shown in the bottom here, in the prairies. But temperature, and in particular the 0-degree threshold, tells you an awful lot about runoff. And so we have a snowmelt-dominated runoff system, as you all know. I've convinced myself that infiltration and runoff generation of snowmelt in frozen soils is the critical problem to work on in the prairies. And at St Denis we have some really excellent data now of the soil conditions for 4 complete hydrological years and counting. And we put in 4 profiles with about 7 instruments in each profile, so that's about 28 points. Of those 28 points, most of the data didn't yield good results, but there were a few and enough to give us some really good data, and here's an example of that. So here we see on the left some water content against matrix potential data from the summer, showing us we have matrix and fracture domain in the till. And on the right we see some temperature versus liquid water content from a single instrument, and that is very valuable data, and it's very clean data as well because it's from a single instrument that's simultaneously measuring both of those parameters. So we can fit parametric models to these data, and this allows us to characterize the soil freezing characteristic curve as well as the soil water content curve. And I've also developed a novel model for hydraulic conductivity in frozen soils, which I call FroSyn, and this basically enables infiltration into air-filled pores, which are present in frozen soils in the prairies at the time of snowmelt. And so you can run simulations with a conventional Richards equation-based physically based model, and this is showing how the snowmelt is partitioned between infiltration and runoff, and ultimately drainage. And so if we look at some data from St Denis, we can see that if we inferred from observations, we see that we have on the top left, we have snowmelt in blue, infiltration in orange, and it's clearly an infiltration-dominated system here, with runoff in green being quite small. Now, when you run a conventional physically based coupled flow and heat transport model, you see a lot of runoff. In fact, almost all of the snowmelt is generating runoff, and that's because there's no representation of the macropores. If we look at my simulation with the FroSyn model, we get much better results. Although they're not perfect, they're moving us in the right direction. So I've rushed through this. There's an awful lot to say about basically fundamental processes and properties of frozen soils, and the field data sets that I've got now are really valuable to push forward some of these ideas, and that's really where my research is focusing in the next couple of years. The other area is groundwater surface water interactions, and this is Edward Bam's work, and I should say the previous work was driven by Sujata. So Edward's been working on groundwater surface water interactions and looking at stable isotopes of water. Here's a quick conceptual model of the prairie profile. So we have weathered till at the surface, overlying unweathered till, which forms aquitards, and then we have these sort of randomly interspersed sandy layers where we have confined aquifers. So if we look at the water table, it would look something like this, and but if we look at the potentiometric surface associated with the confined aquifer, it would look more like this pink line. And so we have these what we call recharge ponds and discharge ponds, and we expect that the flow processes look something like this. And these flow processes would, of course, determine the not only the water balance, but also the chemistry of the ponds and indeed the aquifers. However, when we look at stable isotopes, we see that these so-called recharge ponds have a very distinct isotopic signature to the confined aquifer groundwater. And that doesn't make sense. How can that be if the groundwater is being predominantly recharged by depression-focused recharge from these recharge ponds? So initially we thought, well, we have to reject depression-focused recharge, but then what we did is we started to look at some of the ephemeral ponds. These are temporary ponds that dry out within a few weeks or month of snowmelt, and unless you're looking for them, you wouldn't even really know they're there. But there's thousands of them. And the isotopic signature of these ponds is much more similar to that of the groundwater. And we've also run pond water balance and isotope balance models that show we get much more relatively more infiltration than evaporation from these ephemeral ponds, as of course you'd expect. So basically we proposed this new hypothesis, which is a refinement of the depression-focused recharge hypothesis, which says that the ephemeral ponds are the dominant source of groundwater recharge, and this can explain the isotopic observations in the deeper groundwater systems. And so that's currently being pushed out in water resources research. So this was a very quick presentation because I didn't want to take your time up. Take-home points, I'm hoping to put out new ideas about how to model frozen soil infiltration, which is a very important process for flood generation. We've now got very, very good data sets. If you take nothing else away, know that these data we're getting from the profiles at St. Denis are really driving forward making possible new ideas about freezing point depression and so on. And we've also put out some refined hypotheses about groundwater recharge processes. So it's been a really good productive period. We've got some new things happening and there's plenty more to do. Thank you very much for your attention, and I hope you have a great meeting.